Also going to stop the transcription because I don't feel like that is needed. Mm, Already, it is 4 o'clock, and just so that my schedule does not change, this review will be being posted from 4 to 6 p.m. today on Thursday, September 22nd. This is for DE 2315, Circuits 1, Midterm 1 review. This is a previous midterm Dr. Russell has given me specifically from spring of 2022. This midterm only has 4 problems. Me will be going through 4 problems, and I'll be walking you guys through on how these problems should be solved, as well as elaborate on where these numbers come from and why I'm doing certain processes. My name is Francis, and I'll be you guys' tutor for this session. You guys have any questions for me before we begin? Right now, let's go ahead and get started. So, question number 1. Network 1 shown figure contains collection of resistors and series of parallel connections. The network is connected to a 2 milliamp DC current source to D sub G, J sub G. As shown, you're due ask the following. Calculate the value of resistance to the right of nodes C and D, that is the resistance R sub CD as shown. As part A. Part B, make use of RCD to calculate the value of the resistor Rx placed between nodes A and C. That will cause voltages between nodes A and B, VAB, to be equal to 10 millivolts as indicated. And then part C, with Rx between A and C, calculate the value of voltage V1 across the 8 ohm resistor as shown below. Shall we work and explain in detail all assumptions you make? So, so we're gonna just take in real quick what this circuit exactly is. So first thing I see is over in the top right corner, these resistors right here, here, and here. Those are resistors that can combine in parallel, as we have commonly seen them in this orientation. And then from there, I'm already thinking you might as well combine them in series and then see how low I can get the circuit to be condensed. The reason why I'm not thinking of any main or name analysis is because it's not asking us to find for any specific component, any component's behavior of, say, this this resistor right here, V1, or this one in the bottom right corner. There's nothing of that extent. So that's why I'm not thinking that currently. Well, let's jump right into it. So values of nodes C and D, meaning everything in the past. Here, we want to try and find the resistance for. Well, let's jump right into it. So I'm going to work right side down. So I'm going to work on this branch first, this one second, one third, and then so on and so forth. And scroll on down. So I see for there's the own resistance between this branch right here in the top right corner. I see it in parallel. So 12 is in parallel with 4, in parallel with 6, in parallel with 12. Those are the resistor values there. Those that should be combined in parallel. I'm going to real quick do that. So the formula I like to use whenever it's a larger resistance, not resistance value, but a larger set of components, is really just going to be the 1 over 1. So this one right here, believe you guys have seen this. I'll show it a different way just to show you the math, how it turns out. So real quick, that value should be equal to, let me run the math real quick as I do not have it ready, but because I'm working this live with you guys. First time me seeing this, might be getting my initial impressions. So 2 ohms right here. So we know this equivalent in the top right corner is going to be equal to 2 ohms. The other method I was referring to that should get you the same value is essentially whenever you have two resistors in parallel, just say R1, R2, the equivalent is the product in the numerator over the sum of these resistor values. The reason why I don't really like it for 3 or more resistors in parallel is because whenever you have that, you have to do it twice, you could say. So this will get you some equivalent value there, and then this one will also be in parallel with the final resistor. In our case, since we have 3, which would make you do the equation one more time. It would still get you the same number though. It just really depends which preference you feel like using, which formula you feel like using back there. And I'll go ahead and just show you that hey, this also works for that. See, so the 12 times 4 over 12 plus 4, whatever that is, it should be equal to 16. So that'll be 3 ohms at first, and then that's our equivalent. We'll do it one more time with our 6 ohm resistor. So 3 times 6 over 3 plus 6 equal to is going to be 9, which just says 2 ohms. And to show you that these are equivalent. The formulas you may use just depends your preference and how much time you have, I guess. So in my opinion, this top one right here is the one I would use whenever it's 3 or more resistors. And this bottom one right here is whenever it's just really 2 or less, or 2 resistors in parallel, because there's no point having, using these equations if you're only working with one single key component. So we're going to take this one right here, do the same math for it. So I see them in parallel. It's only 2, so I'm just going to use the second equation I just showed you guys. I'm going to do this, which should get us 3 times 7 10. It's going to get us a fraction, which we're okay with fractions. It's not the end of the world. It just means that not every value we'll be getting is going to be exact numbers, and that's okay because we already see that right here. Hey, there is a 1.9 ohm resistor, which indicates that not all your values are going to be finite numbers. Same thing here, where there is a 0.5 resistor at the bottom between nodes D and E, and same thing at the top. And let me just real quick make sure that I will convert these values over, which should be, I believe, 2.1. I can calculate to be yeah, it's 2.1 crazy. Easy math. Is equal to 2.1 ohms. Okay. So we're gonna go to the next page and just real quick redraw that bench. As I like redrawing it when I was a freshman sophomore level with you guys, where you guys were, I like to redraw my circuits a lot. So this top one should have been 2 ohms, 1.9, and 7. 2, 1.9, and 7. Guess what? It's in series. So it's just a straight summation of them across, which is going to get us it's going to be 10.9 for this entire resistive branch. So if we go back, we know for branch 1, you could say, the total resistive value is going to be at 10.9. And by all means, if you guys have any questions, feel free to stop me, let me know, and we can go through and see where exactly there's a gap in mind. So that's that one. Real quick here, just to show you the math behind it, we're gonna go for branch 2 now. So 12 and 6 ohm resistors in parallel. So for branch 2, you could say it's gonna be 12, 6 in parallel. I'm going to be using the other equations to show you that it's just as viable here. Mhm. 6 is then equal to 4 ohms. Okay, so that's the equivalent of that thing. So right now we have a two resistor values that we know. We know this one is 10.9 ohms for branch 1, let's say, and then branch 2 is going to be 4 ohms. That's what we have currently, but we still need to solve the rest of it before we can combine everything in the grand scheme of trying to solve for the resistor value between nodes C and D. So branch E, this line right here, this line right here, we see 4 ohms and 8 ohms in series. So I'm just going to write over here, this equivalent is going to be equal to 12 because it's just two resistors in series, you add them together. Now, this is where it's going to you might get a little bit confused on what to do with, hey, what about these 0.5 resistors here? What are you going to do? Well, we can go ahead and redraw it to determine what exactly we do with them. So we go to the next page and scroll down a bit. And I'm going to real quick just redraw it. So it's going to be the 0.5 ohms here. We have our first little branch, the second one that we worked out, and then the first one that we did. If I can draw the resistor value, I mean resistor symbol correctly. There you go. We have that. And then we also have our 0.5 resistor here. Okay, so we know it's going to be 10.9. It's going to be, I believe it was the 6, right? Yeah. 2.94. And then 12 right here. There you go. Let me double check the first one just to make sure I didn't do my math wrong there.
So it's 2.1. It'll be 11 total, maybe.
1.9, 2.9. Yeah, that's I think where I'm going wrong. I'm just gonna real quick double check it. Six. Yeah, I was off there. So then that's 210. Oh, okay, I see what I messed up. Let me real quick just confirm the calculation is there. This document will be released to you guys and once when this session is done, so that way you guys can go through and work on the problem yourselves, and also look at my solutions too. So yeah, okay. So this is what we currently have here. Okay, so we have all these values in parallel, all these sets right here, they're all in parallel. And then the 0.5, well, once when we find our equivalent, we can imagine instead of three resistors here, it just be this little system we have where it's a resistor there, the equivalent resistor that we just, whatever we're going to find soon, and the last one right here. This is 0.5 ohms, 0.5, and then resistor value, we're going to go and find real quick. So it's 1 over 12 plus 1 over 4. So we're going to use the inverse value of it just because I mean the original fraction form of it. No, that's not the one I was talking about. That's not it. Yes, I'm looking for. Oh, you know what I forgot to do? I see. Yeah. Okay. Yeah, you were right. So up here, I completely ignored values I was getting. So that's not. So it would be 2 plus 1.9 and then 2.1 here. That's where I was making my
Yeah.
mistake. Going to give you the summation of that, which should get you to 6 ohms instead. That's where I was messing up. Okay, my mistake there. We have that corrected. Let's go to the corrected here. 1/6, and then let's go put it that there. 6, which will get us to ohms again, because guess what? That's the same value we worked with in this top right corner. World comes around in full circle some days. So we know that this is 2 ohms here. So then you just do series resistors in series, which is the summation of this would be 0.5 plus 0.5 plus 2 is just equal to 3 ohms there. Okay, so now we are currently at between these nodes right here. We are currently at the upper limit between where node C and D is. So we are currently right between C and E and D, where my basic point is currently just circling right now. That's where we're at, and the goal is to find the resistor value between those nodes. Okay, so we're almost there. We're almost there. We gotta do just a few more quick combinations, and then we'll be set for part A. The final few resistor operations we'll be doing is just this is node C. It'd be a resistor here. Here's our equivalent we just found. Here's E. Here's that one, and then this one is that node D. This one down here is F. There we go. So you have an equivalent resistor of 2 right here. And then this final one, which I believe was 1.5. Yes, because it's just resistor in series. I'm not going to show that. One at least for this one would be 1.5 ohms. Okay. Guess what? It's in parallel. So we know it's going to be 1 over 1.5 plus 1 over 2, which is equal to oh, not 2, it's 3, my bad. 3 ohms there, 3 ohms here, because math. That would get us to 1 ohm. Now we know between the resistance value between those C and D is equal to 1 ohm. And to show that we've drawn at a page, I'll just show you that this is our equivalent that we just found. Here's node C, node D, and this is one of them. So what we just did was answered part A, where the goal was to find this value of between node C and D. We condensed it down, working from the right-hand side inwards, and we found the resistance value there. So now we're going to use that value to find the value of Rx, which is in this top right corner, top left corner right here. And just to find it, where we know the equivalent voltage is going to be between the equivalent voltage between nodes A and B is going to be 10 millivolts. So let's see where we can go from there. So we know that the circuit is going to be this way. We know that the circuit is going to be looking like this. So we know here's node A, our current source, node B. Here is our resistor value Rx that we don't know currently. And then here's what we just found on our side, which is just the 1 ohm that we just found, node C, node D, positive and negative current is traveling upwards. Current is traveling upwards, where this right here, VAB, is equal to 10 millivolts or 10 to negative 3 volts, however you want to view it. So let's think back to what exactly is going on here. The question is asking us to find Rx, okay? We know our voltage here, and we know our equivalent resistor here, so guess what I'm gonna do? I'm gonna do a quick equation because we also know the current. We also know the current traveling through our circuit, which is ideal for us. It's because that makes things a lot easier. Why? Well, based off KVL and KCL, we know that the voltage going across node A and B is going to be equal to the total resistance times our currents, which is just going to be Rx plus R, which are equivalent. Or our equivalent is this right here. The reason why I say this is true is because, well, we condensed it down. We solved a equivalent resistive value. How the problems are formatted, or at least how Dr. Russell does it, he really wants you to take it one step at a time. So you really can't skip steps in his multi-step problems, which is why you can observe some of the basic concepts and apply them here. In this case, we know the total voltage of this network is going to be equal to, well, current times the total resistance. We know current, we know one of the resistors, we know the other. We can do some quick algebra for it. So now from here, let's real quick do the algebra, which is just going to be equal to the over 3G minus our R equivalent. Going from this equation right here to the bottom one is just simple algebra. By all means, ask me if you want to show the actual steps, but that's what it is. So we know R of X is going to be equal to 10 millivolts over 2 milliamps minus our 1 ohm, which is going to be equal to 5 over 2 units. The real unit ratio is just the millis, but that doesn't matter since they'll be canceling out. So it's going to be 10 over 2. So it's going to be 5 ohms minus 1 ohm, 4 ohms. Now we know R of X is equal to 4 ohms. And then the last question, last one for this question right here, which is what weighted the most with Rx connected between A and C, calculate the voltage of V1 across the 8 ohm resistor. So now we gotta start thinking, well, what tools do we know that can get us V1, which is this voltage right here? Well, we know a couple of things, okay? We can do voltage divider, we can maybe break it apart and do Ohm's law and compare Gauss law just to find each individual voltage across each resistor. In a testing environment, though, we're given higher level tools to analyze this KVL and KCL, Ohm's law. Those are the basics of it, but we have shortcuts, which is what voltage and current divider does. It allows us to proportionally solve for the other components and some of their behaviors without actually having to do each little step to find their respective values. So I'm going to go back to our last page right here. This is for now part C of 1. So now we know a couple of things, okay? So I'm going to draw a circuit again. Here is R of X, node C, our equivalent, our current source going up. There's that, okay? Let's take it back a notch. Let's also add in, so here's C, this is node E, our resistor value here, node F, and this is node D. Reason why I did this is because we know the equivalent. We know our total equivalent is going to be equal to 1 ohm right here, okay, which is between C and D, right? Well, why not work backwards? Because that's what one of these problem sets has done. Because I would be there in the room taking my test. I would reference some of my homework solutions and Dr. Russell's materials, and I would say, hey, in one of his problems, he worked backwards to find one of the voltages. So why not do it here too? This is what we currently have set up. So let's go in some of the gaps. It would be, so this is the 0.5 5 ohms here. If I go on the bottom one there, 0.45 ohms here. And then this one was the 2 ohms that we saw that earlier. Here's the 1.5 that we originally knew, R of X, case of G, where we know here is 10 millivolts, total 2 milliamps for that current source. So there's that. So a couple things we can do. The voltage flowing through this little branch right here first is just going up to the right here, and it's going to equally be distributed to each little branch here, right? Well, we don't exactly know what the voltage is here at node C. But what we do know is using our circuit from above, hey, we can do voltage divider for the first little network. So say this is mesh 1, we can do a voltage divider in mesh 1 from my previous circuit and find the voltage flowing into node C. So let's do that. So what I'm talking about is it would be the voltage divider formula, which is going to be just the voltage going in, or whatever respective node you're saying you're trying to find. In this case, you're trying to find voltage across CD, so it would be across CD, so it would be positive minus, since that's how our convention is going to be set up. And the numerator would be the equivalent that we just found. So there was the value across CD over the sum of our network, the resistive network that we are finding, which is our sub C, G plus R of X, since these are the resistors, which is here. That's what we'll be trying to find, times our actual voltage. Is not a source, but it's a known value that we know. That's why I mentioned the voltage flowing through mesh 1 will also be going into node C and equally distributed across node E. Node E. The difference is, though, R of X will give a voltage drop. Since the component does exist there, we can't just ignore it. It will cause the voltage to drop a certain amount, and that's what we're gonna, and we don't need to figure it out directly. It's just something we have to understand and be aware. So using this little equation right here, we know that the voltage going across the CD is going to be, so our CD, or our equivalent up here, is going to be 1 over 1 plus R of X value, which we determined is 4 ohms, times VAB. VAB is given to us in the problem, which is 10 millivolts. So it's just going to be 10 millivolts, doesn't really matter. So it'll be 1 over 5 times 10. So now we know VCD is equal to 2 millivolts. Okay, so guess what? Now that we know 2 millivolts is being distributed across CD, we know the voltage flowing in is also going to be 2 millivolts. So it's going down up to node B and also to node E. So you can picture it this way. We could say there is some source here that is going into node C and across to the other mesh network that we have. It's ideally the same thing, but where we can label this source to be the value it's found. So it's going to be 2 millivolts is flowing through the circuit. This is node C, this is node D. It's flowing through, so this is the 0.5 ohms, the 2 ohms there, and then another 0.5. So we can do another voltage divider to find this specific network, I mean the voltage across node E and F. As we go back, that is exactly where we want to find it, between E and F. So we have the total equivalent right now. Notice I'm not trying to find the individual voltage currently. That's what we have there. So then we are going to real quick find the total voltage going across E, F. So going back, we're currently here. So we know the EF is going to be equal to, so the resistor we're trying to find right now I mean, the resistor we're using right now is going to be 2 ohms. 2 ohms up top over the summation of it. So 2 plus 0.5 plus 0.5. This is just applying voltage divider where the resistor, the voltage of the resistive component we're trying to find goes on the numerator, and then the sum of however many resistors we traveled through goes on the bottom times our voltage source. In this case, is going to be 2 millivolts. It is going to get us not a good number, but it's okay. It's going to get us 4/3 millivolts. So that's the value we know there. So we're going to real quick redraw the circuit one last time before finally solving this problem. So the final circuit we have currently is going to be this way. Current traveling through there. Here is node A, B, B sub J. R of X is right here. RC. I mean, not RC, but node C there. And here is our 1.5 ohms. 1.5 ohms. We just currently learned that across node CD is 2 millivolts, meaning over here between C and E, I'm going across down to F, all the way over here. Here's the 0.5, 0.5. There. Now, we go back to our previous work in the original circuit between E and F. Originally, there was only the 8 and the 4 ohms. The reason why we used the 2 is because that was our equivalent. There was nothing over to the right side anymore. We condensed it down enough to only have a single component between nodes E and F. Well, how do we get to 2 ohms? If we look back to our previous work, we noticed that we condensed it down. So we have to undo that work to find the original behavior, to find the voltage of V1, which is going across the 8 ohms. We're going to go back and reinstall, I guess you could say, undo the work we did of combining the resistors. So this would be the 8 ohms and the 4 ohms, but we know the total voltage going across this is going to be 4/3 millivolts. That's what we would know there. So the final voltage divider equation we'll be using is we're going to be for V1, so this is V1 right here, is equal to the resistor value that we are using to find, which is 8, plus the summation of it would be 8 plus 4. That is the resistor value there. And then the voltage source we are using is going to be the 4/3 millivolts. It is going to get us 32/36 millivolts. And that is your solution. That's in your solution to part C. So what we did from start to beginning was essentially first acknowledge that we need to find total resistor value between nodes C and B. We went ahead and did a bunch of resistor combinations from parallel and series, condensed them down one step at a time. I repeated the circuit a couple of times just to better visualize what exactly is going on. I even caught my own mistakes and with help you guys. We condensed it down to an equivalent circuit, equivalent resistor value of 1 ohm. So that was answering part A. Part B wanted us to find R of X, some unknown resistor value, but we were given the currents and the voltage flowing across in this final mesh. So meaning if we condense it down to just the resistor value of 1 ohm between C and D, we can do some quick algebra to realize that, hey, we could just find the V equals IR. We arrange it to find R of X, and we get the value of 4 ohms. The final problem had us work backwards and use the voltage divider formula to go ahead and not only find the voltage flowing across one component, but several simply because we need to find the exact voltage we were working with going into node C, which then was going into node E, as the voltage we want to find was in between node E and F, specifically V1. So we had to know the voltage flowing into node E, meaning we have to find the voltage flowing into node C. You guys have any questions for me before we move on to the next problem? I'll take that as a no. So we're going to move right on ahead to the next problem. Question 2, weighted 25%. The network shown in figure 2 is a bridge network driven by two DC current sources. Apply the I shift operation to calculate the value of the voltage VDB. Crucial steps, show the work, show any assumptions you use. So the first thing I want to figure out is what exactly does it mean when it says I shift, So all it's just asking us is, hey, there's a voltage, I mean, there's a current source here. Shift it around somehow. Figure out how you would do that to find the voltage across D, B. So essentially saying find the voltage source as if you were trying to do a source transformation. There's no real easy way though, because it's in the circuit is arranged in the way we haven't really seen. We've seen complex network maps before, but nothing of this shape. So the biggest thing is trying to understand what exactly is going on, So we're gonna try and figure that out together. So first thing I would attempt to redraw the circuit. This is what I'm gonna be doing with you guys. So J1 right here, okay? I'm not gonna put any values in. J1 is there, right? But we know a couple of things already. We know here in the middle is J2, a current flowing to the right and getting split off between node B and node C. And if we look and if we assume the same thing, going as we follow the current going all the way around, we know there's current flowing into node D from the direction of node A and C, which gives us an understanding that, hey, these might be in parallel or something of that sort because it's breaking off on one side and then going around into the other. So something I would do is use the I shift operation that Tom told me and figure out where exactly the current source is located. Because right now, we think, hey, it's connected between R1 through R4 because it is connected between those. But which resistors is it really connected to? That's what we're trying to figure out. So we're going to go through and really see what exactly is going on. So we know from what we were doing. Let's say here is resistor 1, okay? All I just did was change the direction of how the resistors are laid out. That's all I'm doing. Don't be afraid to really redraw your own circuits, okay? I recommend it actually if you really want to see what is going on in a weird looking circuit like this. Don't be afraid to redraw it. Just have confidence in yourself and understanding what exactly is going on. Okay. I think, no, it's not important. We have that. Okay, so this is R1, all right? Well, what happened to R2? Well, if we apply our I shift, we can do one of two things. We can either shift VD forward and say, hey, there's a current source traveling in this direction here and traveling here, meaning we can do a resistor value here with a current source attached to it, simply by shifting it. But how do we know what values to break it apart? You know? We can either do that or do it the other way around, where we have where this is resistor 2, if I got it in, or we can do it the other way around, where there is a resistor here, which is 1 going to some current. That's going to split off. Here is node B. Here is A up here. We found a terminal better. And the same thing down here, where there is a current traveling in here with a resistor there. And eventually it's in the R3. You can do either or I shift, just depends which one you're more comfortable with. For this session, I'll be showing the I shift go across this direction. Okay. Now we know which direction we'll be shifting our eye. So let's try and figure out how exactly that's going to work. Just because we shift it in this direction doesn't mean it's going to be directly related to R2 or R4. It just means we chose to shift it at node B, and it's been split apart into two current sources that we don't ideally know yet. So we know RV is going to be some point. We don't know if it's here yet, but for now, we're just going to claim it's there, and we're going to see if we can solidify a reason behind it. So right now, simply from looking at it, say if it was just simply a triangle of just our node A here, some resistor value there, some resistor value there, and say there was nothing else, okay, just a simple triangle. Here's a little diamond now. Say this was our circuit, okay? The first thing you would think is, well, these resistors right here, they look similar to what we're working with in top half. So let's see what's exactly happening. When we go in, say with voltage, so say there's some positive voltage going through, we go down, it's getting equally distributed between two nodes here, right? And then say if there was some positive current, it's flowing through. Same thing happens here. The current would go ahead and split off into two pieces. Well, since it's splitting off, that implies that there is a breakpoint at node A between R1 and R3. Not 3, 2. There's some breakpoint. That implies that the resistor behavior between these nodes, between R1 and R2, they're parallel somehow. In some form or fashion, they will be breaking apart. With that idea in mind, let's assume this then for now, just for our top half. We assume that they're going to be a parallel somehow, respectively on their own. Now let's apply that same concept to our lower half. So say that the top half is a blank line. So say R1 and R2 haven't sorted out. They're not there. They're just a simple line. And say for our bottom triangle right here, we're only looking at resistor value 3 and 4. Okay, so only looking at this bottom half right here, between 3 and 4, what exactly is going on? Well, using the same logic we applied earlier, say a voltage was traveling down between that we just shot through, and it's equally distributed to points D and B. Well, we know that there might be some interference here with this simple line in the middle, because if you were to follow the same, the same convention of voltage flowing in will get split off equally into the other nodes, there might be some interference as is going to be voltage here and voltage here, Well, this specific case right here, if you look back to one of his examples of Dr. Russell's material school that he provided, and I believe it was source transformations, one of his examples had a very similar shape, not exactly diamond, but there were a lot of diagonals in it, and you guys have worked problem sets too behind that. Well, simply by looking at this, we know two things now. We know that between the B and D, there are also breakpoints, meaning something is flowing out and something is flowing in. So we know that we're gonna go ahead and make B and D have some sort of new flow travel. So we know we might add some resistor here, and some resistor here, but we don't quite know exactly what it is and how this current source is flowing through it. This is where the shifting comes in. Since we shifted it forward here, but we realize that our convention will create an error for us, we can go ahead and just take a few steps back and re-examine how we're going to shift our J2 source across. Since we know between the points B and D, there is some sort of split between the current and the voltage flowing in and out. There's something going on there. We can safely assume B and D will have one connector of our current source when we shift it. Now, from here, we can kind of do a mirror since it is a symmetrical circuit. Like just simply looking at a shape, we can also make our circuit similar to that. So now we know that we got that line there. Here, so here is A, here's C, here's our original source. Nodes D and B, well, all that's missing is how R3 and R4 are connected. Well, from our shifting operations, I say it's safe to put the current source going down here and the voltage, the same current source going up here. Because all we really did is you can do either or. Because when what I just did is essentially shift one current going down out here. Not for I1, but for I3. It's going down into it. And then I said the current of the positive or the negative side is going to be flowing down into R4. These I shifts operations on the left and right hand side are also valid, but doing that creates a discrepancy whenever we examine the behaviors just from a conceptual point of view, meaning that the current we assumed of how it was traveling wasn't ideal and it was going to create a convention issue for us in the future. So that's why I went ahead and flipped it and created this circuit instead. But wait, what happened to our original source? Like what happened there? Because if you notice here, something's not quite right. We know this is J2, we know this is J2, R4, not putting the values yet. What exactly is VD? Well, VD is just trying to find the voltage across these 2 points, right? That's what the question is asking us to do. Find the value of the voltage of V across nodes V, C, and D, which is right here. Well, something that I missed, I realized that the behavior of J1, all of this between nodes A and C isn't just a simple direct parallel connection. The biggest thing that I made a mistake of there was, yes, we can assume that, but it'd be easier for us to go ahead and say there's a connection here that's been shifted over. So what I'm doing is right now is looking back and saying, J1 isn't as ideal as I want it to be. So let's split it off. Same thing we did with J2, how we made it 2 sources using our I shift. Let's do the same thing for 1 and 3. So all I'm doing is saying, hey, J1, we're going to split off into 2. So there's going to be a current going down into here, which is going to be J1, and then 1 also going from here, which is going to be J1 as well. So using that logic, we can shift it over in the same fashion we did for J2. And this is going to be the equivalent circuit we'll be working with. Redrawing circuits is something that is difficult, honestly, if you're not quite familiar with the basic principles behind this. So if you're having issues redrawing a circuit, I would say look at some examples Dr. Russell has, where he redrew his circuits and figure out why he did it the way he drew it. So from here, we have our new circuit that we'll be working with, okay? Well, we can see a couple of things now. We can see that, hey, R3 is in parallel with J2 and R4 is in parallel with J2 as well. We also know that J1 is in parallel with R3 and J1 is also in parallel with R1. Well, we can do a source transformation with both of them actually. So what we're going to do is do some quick source transformations. So J2 is in parallel with R4, meaning our new circuit is going to be a resistor with a DC source. It's in positive here in R4. Well, it's just some simple Ohm's law. So in this case, to find our voltage is V is equal to IR, just doing that quick multiplication. We know originally 15 milliamps, so this is 15 milliamps here and here. R4 is 2.7 k ohms, meaning our voltage here should be equal to, if I can set my calculator to not spit out fractions at me. Give me 1 second for that. Okay. Our voltage of J2 has been transformed into the current of J2 has been shifted to a voltage source using resistor 4, which created a voltage source of 40.5 volts. So that's what we're going to put here. There's that. Similarly, we're going to shift over R1 with J1. So J1 is in parallel with R1, meaning it will return to us a resistor. Return to us in the other direction. A resistor with a voltage source, just like that. This is R1, where R1 is equal to 4.3 kilo ohms. So same thing again, using Ohm's law, we can real quick find the voltage going across there, which is just simply going to be 10 times 4.3. Guess what? It's 43 volts. So it's going to be 43 volts here. Okay. Well, so now we have this equivalent circuit here that I'm going to redraw on the next page because we're running out of there. So this is our current equivalent circuit. We have currently have this resistor here with the voltage source we just found. This is still R1. This is the 43 volts. Simply by doing R1 times J1. Here we go across. This is simply R2. There was no current source attached to R2. Here is node E. Here is node B. For node B, we know we do a source transformation to get a voltage source. So here is R4. Up here is 1 ohms. Down here is going to be R4 times J2, which gets us the 40.5 volts. But what about in the bottom corner? Well, let's look at what that is in the bottom corner. So we know R3 is in parallel with 2 current sources, J1 and J2. The current sources are traveling in different directions. So we know from previous work that current sources in parallel simply means this is I1, I2. What we're saying is I1 is equal to, is summed with I2, and that is the current sources in parallel. And just super for review, voltage sources in parallel just means that if they're equivalent, so say this is V1, which is equal to V2, it just means that, hey, your equivalent is just equal to V1, V2, where one would get sorted out. So you would go ahead and get a singular voltage source in parallel. In series, it's the opposite. You would do the summation of it. And for current sources in series, it's similar to the rule of sorting out, where if the current sources are equivalent in series, you may short out one of these sources. If you are unsure about those principles, again, and materials 2, Dr. Russell has given his own work to clarify. It is wordy. I will admit that, but by all means read it, and you'll get the gist of it from his diagrams. If not, by all means come visit me or ask the DJ Justin to go ahead and clarify that, or to work with me, either or. But continuing this review, so we know the current source J1 is equal to 10 ohms going one direction, and J2 is going the opposite direction. So we can find the difference of it and claim that, hey, this voltage source down here is going to be R3 times whatever difference J2 and J1 is. And what I mean when I say that is we know a current source is traveling there. He was the resistor. And here is the other current source that was traveling in the opposite direction, where this is J2, J1, 10 milliamps, 15 milliamps. Well, just find the difference. It doesn't matter what value you get. So say I wanted to do 10 minus 15. You know it's going to be negative 5 ohms. Well, the sign just indicates what direction it was going. Since this is J1, J2, J1 gets taken out of the picture, and all left with is J2. So our equivalent circuit is going to be voltage going positive, not like that. I'm going to redraw this real quick. It's going to be R3 J2 minus J1, where the voltage is traveling downwards. That's where the positive lead is going to be. There's that. So now this is our equivalent circuit that we're working with. From here, we can do a few more combinations. So this is what I see. After looking through some examples of Dr. Russell and some homework, some previous problem sets, we know that, hey, these resistors, they're all in series. We can add them up. And the same thing with these voltage sources, where, hey, they're in series. We can add them up and see if there's any differences. The real key note is be careful on which ones you add up, because the goal is to find the voltage across B and B. Okay, so what's going to happen is I'm only going to combine. I'm going to draw a little line here. I'm going to get what's happening. I'm only going to combine the top half with itself. So this little network right here, I'm only going to be combining anything that's possible in that, and respectively with this little network down here, same thing. We're going to combine anything in there. Oh, and I forgot to actually show the exact calculation to find our voltage source for resistor 3. That value should be just, so 5 times resistor 3, which is 2k ohms there. So just 5 times 2 is going to be 10 volts here. So going down, we're going to start with the top half. So the top half I'm referring to is going to be specifically R1 and R2. They're in series. We're going to do the combination of that, where R1 is 4.3K right here. So all I'm saying is this is going to be some resistor value of R1 plus R2 going across, saying, hey, there's a voltage source here, and then here's node B. That's the top half. The bottom half is going to be very similar. All we're saying is, hey, there's some resistor value that's going to be sum of R3 plus R4 because they're in series, and then some voltage source, whether it be in this notation or not. We're going to correct that if we have to. There's that right there. I'm going to go ahead and figure out these voltage sources now. So look in the top half, there's only one voltage source. Positive lead is on top. So the way we do it is correct. It's going to be 43 volts traveling with the positive side facing the right side. Bottom one, same thing. The voltage is flowing in the same direction. So positive lead, so positive is going to the negative side of our 40.5 voltage source, meaning we do combine them in series. We do not subtract them. So our total voltage source here is going to be 50.5 volts. Positive lead is going to the right. We know series resistors in series is just the sum of them. So the top one is going to be 5.3 k ohms. The bottom one is going to be 4.7 k ohms. And there's that. Well, what do we do from here? Again, the goal is to find the voltage flowing across VD. Well, how can we simplify this even more? We can do one of two options. We can either recombine these voltage sources and see what happens, but guess what? The other option is to go ahead and retransform these into current sources to go ahead and see if there's any behaviors we can examine from there. I'm going to show both ways. Well, I'll show one method actually, and that method will be to, I'm going to go with transforming the voltage sources into current sources. So what I'm saying is we're going to transform this. So we have a resistor in series with voltage source, meaning we'll be getting here is going to be D again. Is going to be a resistor in parallel with a current source. In this case, we know it should be traveling this way, right? That's for that one. And then for the lower half, same thing. We know it's a resistor in series with the voltage source, meaning the output we'll be getting is a resistor in parallel with a current source traveling to the right. There we have it there. So simply just by doing Ohm's law again, we keep the same resistor value because that is not changing. What is changing is our source, simply by doing V equals IR, or in this case, I is equal to V divided by R. We know that from this voltage, this current source here, it is going to be 43 over 5.3 K. That was going to be, I believe, it's going to be like 8.132 milliamps. Don't worry about the number itself. Again, this is just a calculus, so using whatever numbers he feels like. It's not always going to be clean whole numbers. Just be aware of that. Same thing down here is going to be very ugly numbers. It's going to be 10.7 or 4 milliamps. Depends how far you want to go. Doesn't really matter too much. So there's that. But hey, guess what? We can do a quick combination of these. Of these right here. So we know from earlier current sources in parallel. We add them up. So from here is going to be it doesn't matter which direction you feel like adding the current sources. It really doesn't, as long as you add them up correctly. I'm moving it to the top. We have a current source traveling here over to the right, in parallel with our resistor. Here is node E, and now we can just say, hey, down here is voltage across V. Now, what about this resistor value? Well, same thing. We can see that the resistors are in parallel with each other. So when I real quick do that, I'll actually show you real quick. For that, 4.3 plus 1.4.7. Your units, again, just be wary of them. You don't have to always write it out. Just be aware when you are doing the actual calculations. If you do need to write out the units, by all means go ahead. I preferably don't do that anymore just because I feel like it covers up the work. But we know that this is equal to 2.491. We know this is kilo, so it's going to be kilo ohms. Sorry for the mess there. Then probably point out how this circle is going to be drawn, but that is fine. So we know down here 2.491 K, and this is going to be just a summation. The current source right here, value equivalent, is going to be just a summation of it. So it's going to be 18.857 milliamps. Again, it's up to you how far you want to go. The farther out you go, the more decimals you'll be adding just to show numbers. It really doesn't matter as long as you're within a few decimals of the correct answer. So finally, voltage across VB is just equal to the current. So 18.857 milliamps times our resistor value, or 2.491 kilo ohms. We get a value of, it's going to be 46.975 volts. The reason why it's just volts, again, it's units. This is 10 to the negative 3. Kilo represents 10 to the positive 3. They cancel out. It's just good old regular volts. And as your final answer, 46.975 volts. The biggest mistake I made here originally, and I had a similar problem to this. The biggest thing was redrawing your circuit. Don't be afraid. Don't be afraid of trying to redraw it. Take it one step at a time. Practice by all means, redrawing some of your guys' circuits from previous problem sets. Look through his examples. That's what I considered there. And then be familiar with your I shift operations, because this is the topic you decide to cover for problem set 2, coming for midterm 2. Not midterm 2, midterm 1 of spring 2022. So the semester previously. Do you guys have any questions for me? If not, then we'll be moving forward to question 3. This one is a fun one, honestly. I thoroughly enjoyed this one because this one's pretty straightforward. So all we're doing here is simply given some resistor, batteries, currents, everything. We want to find a couple of things. Okay, we want to find R val. So currently this is unknown. It's unknown, but hey, we're saying we want the current of our load to be equal to 530 ohms. And it gives us the hints. We use the source transformations, source combinations, and resistor combinations to reduce it to get an equivalent of AB. Show your work and such. You guys had a problem similar to this, which was Norton's equivalent. Really, the first thing I'm gonna do is ignore that load. I'm gonna say, hey, it's not there. Let's only look at our current circuit, see what we can do with it. So let's see what we can do with it. And also notice where he places his nodes. That helps out a lot in the future as he guides it, as he likes to guide it. Dr. Russell likes to guide us in our starting point and where exactly we should begin in the circuit. So first thing I see is, hey, there is a couple things we can do. We have R2 and J1. They're in parallel with each other. This is in series, but I want to combine it in parallel. So I'm going to do a source transformation for R1. So I want to do basically this right here. I is equal to V over R. So I'm just going to say that there, which is going to get us 10 milliamps. Okay, so there's that. And that's really the only big combination, transformation I'm going to do there, for now at least. So we know this now. So I'm going to redraw the circuit and go over here. So we know it's going to be a current source here, resistor here, in parallel with this right here. Our current source going down. This one should be going up, just like that. And I'm going to ignore the rest of it for now. I am going to fill in some of their positions though, just so that I am aware of what is around me, what's left to combine, I should say. I'm not going to work with it yet. Here's that, okay? So from here, we can see a couple of things. We can see, so this is R1, R2, J1. We're just going to keep this as 10 milliamps. I'm not going to label anything. But here we can see this is J2, this is R3, this is 33 milliamps right there. Okay, this is what I would go ahead and combine R1 in parallel with R2. Why is in parallel? Well, if you were to break apart this specific branch right here that contains R2 and J1, you would be able to inspect it essentially from looking at it and comparing it to previous problem sets or his examples. You can safely assume that, hey, those are in parallel. We can combine them that way. Same thing with our sources. So we know in combination, not in combination, in parallel, current sources are just added up. If there's a difference, figure out which direction the current's flowing. So we know it's going to be 10 minus J1, where J1 is 2 milliamps. So 10 minus 2, 8 milliamps. The bigger source was our 10 milliamps, meaning J1 is going to get taken away, and the left-hand source is going to be left over. So let's real quick actually show that. Then just to show this, R1, R2 is in parallel. I'm going to, for this one, I will write out the formula. I'll use the product of one, just because I feel like being different. 3 times 6 over 9 is equal to 2. Okay, there's that. So again, when I was back in this course, I love to redraw the circuit, so that's what I'm going to do. So it's going to be a current source going up, current source going up, resistor here, voltage source. We haven't worked with that yet. We haven't worked with anything down here either, so that is kept the same. Current source going to the right. And then I'm going to go ahead and add in the rest of the circuit. There's that, and then guess what? That is, well, that's all that stuff. So we know earlier 10 minus 2, it's 8 milliamps. So here's where the 8 milliamps would go. R1 and R2 they got combined in parallel for 2k ohms. So that is left. And then we're going to go ahead and fill in the other bits and pieces. So this is 34 volts. This is, I did that accident. It's going to be R3, which is going to be 2k there. And then J2, which is going to be 33 milliamps. And then this is J3, which is 10 milliamps. Okay. So from here, again, we're trying to figure out a equivalent circuit, something smaller we can work with. So as of now, I see a couple of things, okay? This little branch right here, this is going to be in parallel with each other. R3 and J2 are also in parallel with each other. And then we'll see what we can do with that voltage source when we finish those source combinations. So let's figure it out. Redraw it again. So this is some node right here. I believe that's where C is. Yep. So this is where C is going to be. All we're saying is, hey, that 2k ohm resistor is now here. We transformed it with our 8 milliamps current source. And we should get a voltage source with a positive lead on top, as that is where the arrow notation is, and that value is just straight ohms law of V equals IR. So 8 times 2 is 16. The units cancel out, so just little 16 volts. Here is node D. And then click to the right side. This is, I've been untouched still. We have not done anything. I believe this is E2. And let's go up, just double check that. That is the case. E2, which is just a positive 34 volts. That has been changed. Down here, we will do a source transformation again. Series, in parallel is a resistor and current source, meaning we should get a voltage source in parallel with the arrow facing to the right side, not parallel, in series with the resistor. And then here is the untouched current source that we haven't used yet. Here we go. So from here, again, we just need to go ahead and combine these, see what we can do. This is also 2K there, 2K there. This bottom one, well, let's figure it out. It's going to be the same thing, so V is equal to 3 times 3. Units cancel out the 2K ohms, not 2K ohms, that's not 3. Max it there, it's going to be 33 times 2. So this is milliamps, this is kilo ohms. Units cancel out, so you just get 66 volts. Which is what we have here. 66 volts. So from here, I'm gonna explain how this left-hand side is in series. You guys like to jump the gun a little bit and just assume that you can maybe work with the current source first. Well, it's not exactly clear what the behavior is, as when you see here, there's some, say, we shoot the current source through. Okay, so this current traveling through R2 to the other sources, and then same thing up here. Well, whenever we do try and use that notation, you're saying current is going in, going out. It may not be as obvious, but this behavior does indicate that we can't quite do anything with I believe that is J3, yeah, J3 current source quite yet. So let's work with what we do know for now, and go work with the other voltage sources that we just worked with. So to finish off this, the equivalent circuit is just gonna straight be in series, so 2K resistors in series, and then same thing with the voltage is in series as well. So you just do the summation of it. If there is any conflicting orientations, do the difference of them. What I mean is specifically here. So voltage source there, and there. There's only 2 of them that match up, E2 and the 16 volts. They have proper orientation. You would add them together. This 66 volts, though, is facing the other way, meaning there is going to be a difference. So this is going to be 66 volts minus 16 volts minus 34 volts. That's going to get us 16 volts. It doesn't matter which order you do. You just keep in mind the sign conventions. So say if we did say 16 minus 66 plus 34 instead, something kind of like that instead, you would still get negative 16 volts. It's just the orientation would be different. Just keep that in mind. So I am running out of room here, but let's move on to the next page. So all we're going to be doing here is essentially redrawing it one last time. And we resistor here, some voltage source we do know it's going to be 16 volts. We know from the previous page that K is just the equivalent resistor that should go there is just the 2 plus the 2K ohms plus 2K ohms is going to be 4K ohms here. 4K ohms there, 16 volts, and then hey, look at that, we convinced it down pretty well. And then one final source there we have to do to A and B. There's that, which is 3. So then we can do one last combination transformation. These are going to be equivalents. And find our current source. Since the positive is on the bottom, we're going to show that the current is also traveling downwards. And the resistor is going to go here. And then our current source is going to go up because J3 has not been touched yet. And there we go. How do we find the current value for this one? Again, I is equal to V over R. So this be 16 volts over 4K. The 4K means we will get milli because it's dividing by 10 to the power 3. So it'd be 16 volts over 4K is going to equal us 4 milliamps, and that's our value we have here. We have 4K ohms there, and we 4K, and then J3 has not been touched yet, and we have nodes only. Well, we know, I've been repeating it several times, so hopefully you guys know by now too. Current sources in parallel, we do the summation of, so it's going to be 10 volts. Say, it doesn't really matter again, just be aware of your sign. So it's going to be 10 minus 4, or you could do 4 minus 10, doesn't really matter either or. The value we want is 6 volts. If it's negative, that just means that, hey, whatever source you label as the bigger one isn't actually the one that's going to be used. It's going to be the other one. It's going to be the orientation of the bigger source. So both of these just mean that we'll be using a current source that is traveling up, which would be in this right here. This right here, current source, or resistor. Here's A, here's B. This is 4K ohms here, and this is going to be 6 milliamps. And then, hey, that's our equivalent. But don't forget, that's not the goal. The goal is to find equivalent. The goal is to find some resistor value that will get us a current load of 5/3 amps. So we're given a constraint. We want to find the unknown with that. So all that's saying is, hey, now put a part here. That is some R. And we know current traveling through our R valve is going to be 5/3 amps. Well, in this orientation, we have a current source and 2 resistors in parallel. The tool I want to use now is going to be a voltage divider. But the voltage divider equation that you guys are, well, I'm going to write it first, is going to be using JAB, which is just this one right here, because it's the current of that. So JAB is going to be equal, actually, it'd be easier to find the other way around, my bad. So I of L, that's the goal, right? Current divider, same thing as voltage divider. We're going to proportionally try and find the current traveling through one of our components, in this case, RL. So we know RL is the one we want to find, right? So I'm going to put it up top, is what you would think. And that applies to voltage though. So let's think about it. So I'm going to make you guys think about it conceptually. Okay? Say the same orientation of some other circuit. Say that there is 2 ohms here, there's 2 ohms there, and then somebody just a value of 5 ohms here, right? The current traveling through 2 will be greater than the current traveling through our 5 ohm resistor here, because 2 ohms that provides less resistance, meaning more current is going to be traveling through, which is where we drive that in the numerator, you put the component of you put the resistive value of the one you don't want to find. whenever they're in parallel like this. So instead of putting RL, I'm going to put the 4K here instead. 4K, or in this case, RAB. I'm not going to work with the values quite yet because I want to go through this conceptually. You know, at the bottom, same thing as current as voltage divider is the summation of them. And then our current source, in this case, it will be JAB, right? And that's I of L. We proportionally solve for it. But wait, the goal is to find our resistive load. We already know IL is going to be equal to 5/3. 5/3 amps. So solve for RL. That's what we're going to be doing. Algebraically speaking, some real quick, run it through you guys. So you would multiply it. Multiply divided JAB across, so it'll be IL over JAB. First step, then multiply by the denominator of that, or you can do the inverse of it. So you get this times RAB is equal to RL plus RAB. And then one last quick step, and you have RL is equal to RAB of IL minus 1. You can distribute it, you cannot distribute it, it is your call. However, you want to solve it algebraically, just the goal is to find RL. This is my method, your method could be different, still get you the same answer. Does not really matter how you feel like solving it, but now let's go ahead and plug and check. The RL is equal to RAB, which is 4 ohms, 4K ohms, so 4K carrying units here. The top, the numerator is JAB, which we got to be 6 milliamps. The current at the bottom is 5/3 amps. Nice one. So let's see how this is happening. So 4K times, this is 18. So all I'm just going to do is, flip this right here. Just going to flip it. So this is just going to be 6 times 3, which is 18 over 5 milliamps is still on the top. Move that there. And then we're just going to carry it through. So we know that our end units is going to be in the range of kilo. So what we're saying is, hey, this is going to get us a total, resistor value of RL is going to be equal to 3.985 kilo ohms. The calculator did spit me out a negative, but don't worry about that. That just means the orientation, wherever we had it in, just means that the orientation is just simply, I don't want to explain this. Yeah, the orientation should just be flips, right? Because a negative resistor value doesn't really exist. All that just means is the value should be across. Let me actually double check my math before I continue. Because I could have swore earlier it's not supposed to be spitting out a negative value. Am I having something wrong? We will find out together. Oh yeah, I do something wrong. I am crazy. Miscarried units was supposed to be 10.4. 10.4 kilometers. If honestly, units and circuits isn't something as important, you could say, in other engineering majors. If when you guys take a class called MAE 3309, it's just thermodynamics and mechanical based engineering course. You guys they emphasize a lot on units and circuits. Be wary of them. You should know what units will be expected. In this case, we're working in kilo ohms. We're most likely going to expect our results to be in kilo ohms. I made a mistake here when I put it into my calculator and tried carrying out some units. I made a mistake there. Just be careful when plugging into the calculator, but this is our final value here, 10.4 kilo ohms. So to recap what we just did, question asked us to find a RL value, an unknown load with a known current. So I put a constraint on this of 5/3 amps. First thing I thought of is might as well condense the circuit down to something that's easier to work with. We did various source combinations, transformations, resistor combinations to go ahead and condense it down to a equivalent circuit here, right here. And then using our current divider formula, we solved for our RL value to be 10.4 K ohms. Yeah, you guys have any questions for me? Moving on to the final problem, because this question in this midterm only had 4 problems. Well, you look at that. The resistive network shown in figure 4 contains a VCDS. This basically means there's going to be some sort of dependent sources in our circuit. Right, the full mesh analysis and matrix equation main in numerical form, express this equation in usual formats, where it just says that, hey, I then is I am into 4, it's not the main. Dr. Russell, he may toss you a name or name problem. In my circuits 1 class, when I took it back in the spring of 2020, we did get a name and a name problem. Just really depends which one he feels like it. He could be testing you guys over one or both analysis tools of analysis. So is be aware of both name and name and how to set it up, which is what I'll be doing here. But differences though is he will usually not give you the option of regulating your meshes. Why? Because he wants to test you on your understanding, not if you can set it up right, but if you can go through the motions of it correctly. So we're going to go through and just start doing the mesh analysis. So I'm going to start by just simply writing out the basic equations of what's going on in each one. The I1 is all we're saying is, hey, the resistor value, my bad. We're out of water. It's going to be a total resistor value. So IM1, the current going through IM1 times R1 plus R2 plus R3 is equal to our dependent current, our independent voltage source. But hey, you guys today, this Thursday, went through a lecture that we clarified a little bit more on dependent sources. So I'll go ahead and separate that out here, but I will elaborate a little bit more later. So we know RMI7 is going to be subtracted by our EG. I'll elaborate on that in a bit, but I'm just here trying to set up each individual main equations of what's going on in each little mesh right now. So mesh 2, IM2 is going to be just again go through, apply KVL, KCL. In this case, mesh analysis specifically works with voltage sources. Everything we see here is already in voltage sources or dependent voltage sources, so we didn't have to do any source transformations. Be wary of them though, that you might have to do some source transformations before starting your name or your main. In this case, we're fine. IM2 is going to be just the sum of each one, so it's going to be R2 plus R4 plus R5 plus R6. Hey, there is a dependent source though. And here it is right here. So it's just going to be RM I7. Great. Same thing. IM3. My bad. Okay, IM3. Same thing. Going to go through R3 plus R5 plus R7 is equal to 2 volts. Or actually, I should be better to put it if I can erase EG. There's that. There's nothing else there, right? There's no dependent sources. There's nothing else. And then the final equation, the main equation I want to write down is IM4. So IM4, I'm going to look up here, see if there's anything there. Nope. So it's going to be this IM4 times the resistor value of R6 plus R7 plus R8 is equal to, well, if our current is traveling through clockwise, meaning that our dependent source is correct. Our dependent source is correct, so it's going to be mu V2. This is a dependent voltage source, meaning the mu V2 is just dependent on the resistor 2. Now, to elaborate a little bit more now, the reason why I subtracted EG from RM I7, so the dependent source in mesh 1, is because it didn't follow the current flow. So what I mean when I say that is whenever we draw our current is traveling through the circuit, our dependent source had proper orientation where current was flowing into the negative side and coming out of the positive. If we apply the same thing going down to EG, our voltage, our current was flowing into the positive side of our voltage source, meaning it went against our convention, so we have to subtract that from RM I7. RM is just some value, it's just 4, so really it's just going to be 4 I7, and I'll write that in later. But these are the main equations I wanted to write down first, okay? So now we're going to start setting up main. I'll take it one step at a time since this is still pretty new to you guys as of 9/22, because your guys' exam is next week. So mesh 1, the first thing that goes here is the total resistive network. According to Dr. Russell's materials, which I really recommend you guys read, it's really helpful in understanding how to set up name and name. Again, a little bit wordy, but it will get the job done, especially his simple examples. They really help. So the first element, the first number we put in row 1 is going to be just a sum. So it's going to be 1 plus 2 plus 2, but we originally wrote here. So this is just going to be, what's that? Mu 5. The rest of the components is essentially if there's any shared components between mesh 1, we're going to write it as a difference. So when I'm going to say that specifically, so say we assume that, hey, oh, this is right. Between mesh 1 and mesh 2, is there any component being shared? In this case, it's R2. R2 is being shared, so we write that as a difference between them, which is just going to be -1. Now we apply the same thing here. Between mesh 1 and 3, guess what? It's R3. We're going to write that's a difference there. But hey, between mesh 1 and 4, there's nothing being shared. So what y do we put? It's going to be 0. So following we just did is going to be -2 and 0. And that is our first row done. Next row, so mesh 2. Mesh 2 is going to be this again, the sum, so same equation right here. We're going to use this real quick. So it's going to be R2 plus R3, R2 plus R4, R5, R6. It's going to get us a total of 9. Right? So make sure for the same thing. Yeah. 9. So 9. And put it right here. Wait a second. That's not where it goes. A good tip I'm going to tell you. Well, you'll pick this up too. Dr. Russell has said it already too. I viewed his lecture just to make sure he gets the proper tips across. The diagonals of each in each row is going to be the sum. So this is where the sum would go. The 5 up here represents the total sum in mesh 1. The 9 right here represents the total sum in mesh 2. We're going to go ahead and do the total sum of mesh 3 and 4, just so that we can get those out of the way. So mesh 3, R3 plus R5 plus R7, 2 plus 4 plus 2 is going to give us 8. So then that we go here. And then abiding by the same rule, we're going to go and find the total resistive sum in mesh 4, 1, 2, and 3. It's going to get us 6, and we have those done there. Now let's figure out what is being shared between mesh 2, 3, and well, between all the meshes, because we have to examine all of them either way. So let's start. So we're currently looking at mesh 2. Okay, for mesh 2, between mesh 2 and 1, we already know there's one component being shared, and that's going to be R2. So we're going to write that there for our first component. Between mesh 2 and 3, there's one component being shared. It's going to be R5. That's going to be in one of our slots for the 3 for mesh 2. And finally, between mesh 2 and 4 is going to be between these two meshes. There's one being shared, R6. That's also going to be inputted as a difference. So let's go back. Let's go back and fill those in. So it's going to be -1 here, -4, and -1. Again, just to show where those numbers are coming from, all you're looking at is is there a shared component between the two meshes you're currently observing. So it would be 2, 4, and 1, which is what we write respectively for mesh 1, 3, and 4, which is the difference of those. -1, -4, and -1 again, which is what we're kind of doing here. Same thing for mesh 3 and 4. Again, we're currently looking at mesh 3 right now. So we're saying, is there any shared component between mesh 1 and 3? There is. It's R3. So we will put a difference of -2 ohms there. And the same concept would apply between mesh 2 and 3. These are the shared components right here, not that one. This one right there. So it would be a -2, -4, another -2. That's what we would be writing there. So a -2, -4, and then a -2 again. Finally, we're on our last row where we put the sum in. So we'll look, is there any shared component between mesh 1 and mesh 4? There isn't. Down is going to be 0. Between mesh 2 and mesh 4, we already know from filling in our previous rows that R6 is being shared. And when you're working on the later rows, it'll become a habit to kind of look at your previous numbers and realize, hey, between mesh 4, there's a shared component of R7 and R6. Between 1 and 4, there is none. So that'll be 0 there. So it'll be -1 and -2 respectively. So in order, between mesh 1 and 4, nothing being shared. 2 and 4, it was -1 and then -2. And that is our resistive map, our RMP. But that's not what the equation says, right? We still got to get it in a form. We're still working with it, essentially. You guys saw an example earlier today. You know that we're not quite yet now. Just writing in our mesh vector. Let's say something like that. Writing in our mesh vector. 4. There we go. And then now this is where we write our original values right here. This is why I like writing. This is why I like writing out the basic KVL rule for each mesh, just the one that gets the basic behavior across for each respective mesh. This is what we'll be writing in. All this is going to be put in our E sub mi, which is just a final form of our vector for our sources, essentially. It's not quite. My bad. I'm going to say this is E sub m. My bad. So I'm going to go over here. Really just take it line from line. R1, 7. Minus E. This is just negative since it went against our voltage. Oh, what's the negative? Yeah, I did not. Let me write it in. So, reason why I'm putting in for mesh 2, the reason why I'm putting in a negative is because we already wrote it down for mesh 1, okay? Plus, not even that. Yeah, my bad. Not even that. We're only going to be looking at mesh 2, okay? Ignore everything else. We're saying the current is traveling in a clockwise orientation. So it's traveling around here, here, and here. Guess what? Our dependent source, RM I7, is going against our current convention, meaning there will be a difference there instead of it being a positive number. Similar to what we did originally for this one right here. We noticed that, hey, R of M I7 is flowing with the current, but EG isn't, which is why we wrote it out this way right here. I should have the negative already. My bad for missing that out. Everything else is correct though, and I will double check that just to make sure. Mu V2 there. So let's real quick double check out our sources. So current flow for ion 1 traveling through in a circle clockwise is our dependent source I7 is correct. EG is not. That'll make that negative. Ion 2. Same thing here. Our dependent source is not flowing with our current convention we set. So make that negative. Ion 3. This one is though. This convention for EG is following our mesh direction of the current flow. So make that positive. And then same thing here for ion 4. Current is flowing into the negative and coming out of the positive node of our dependent voltage source, meaning that's also going to be positive there. So this is our current map right here, where this is I of n and this is E of n. Well, based off what we currently understand, we need to substitute in something. So specifically, we have to substitute in something for I7 and V2 in terms of knowns, values we do know. Because as of now, these are variables that we don't know. These are values that we haven't found yet. So let's look and see what exactly we can do. Go back to our circuit. So I7, where is I7? I7 is right here. What we do know is, well, it's shared between mesh 3 and 4, right? So that means whatever current is flowing between these two nodes is just going to be difference. So I7, this really means it's going to be the difference between mesh 3 and mesh 4. Same thing with V2. Where is V2? Well, we know it's going to be the top of point between mesh 2 and mesh 1. So let's see real quick what exactly is going on over here. Well, V2, we know voltage is equal to current times R, right? Well, resistor 2 is the value that we know, right? So V2 is equal to R2. Well, what about the currents? Same thing. It's just going to be a difference of between mesh 2 and mesh 1. And in our case, because our current flow is traveling, the one that is traveling against our dependent source is going to be IM2. We're going to list that first. We know our convention here, and for our other dependent source here, this convention right here, if our values come out to be negative, all that means is our convention here, we assumed of our mesh difference is just the other way. Meaning we were supposed to do IM4 minus IM3. But right now, simply just from observing our currents, the one flowing against it, the one flowing with our current is mesh 3. So we're saying, hey, that's going to be positive. And then the one flowing against it is IM4. There's that. Over here, our current flowing through our dependent source, the one that is following the correct convention is IM1, meaning we'll use that as the lower value and just say mesh 2 is going to be the bigger value. If you're confused on why we're setting up that way, again, I would really recommend to go ahead and look at Dr. Russell's main examples and his detailed explanations in the materials. They help out a lot. They really do. So our final equations we have here is going to be IM3 minus IM4 R2 of IM2 minus IM1. That's all we have there. So this is what's going to be happening now, okay? Everywhere we see I7 or V2 in our even vector, we have to substitute in our knowns now. So that's what we'll be doing here. So we'll be going from, this is what we'll be going from, it will be minus 2, negative R, minus 7, we have a habit of writing 7 over the also it is there, so we're going to substitute in I7 and V2 for the equations we just wrote. So it is going to become something a little bit bigger. 3 minus I4 and then negative R and 3 minus I4 0. I will explain that here shortly why that's a 0 there. And 2 and so according to Dr. Russell's materials, the final vector form we want to have is where we separate the dependents. So these are all our dependent sources, and we just add it together with the independent sources. I can spell. Independent. So then we know from our original equation we wrote that EG was involved in mesh 1, and we said that is a negative because it was going against our convention that we set for a mesh. In mesh 2, there was no dependent source, so that would be a 0 there. In mesh 3, there was the appearance of the original source again. And then in mesh 4, there was no independent source, so we say that's a 0 here. So all we really just did was figured out a way to substitute I7 and V2 into our mesh values that we're working with, and substitute those in and separated out the dependent from the independent sources. And that's what we did here. Now we're getting close to actually solving out our mesh. So according to Dr. Russell's equations, this is the final form we're supposed to get it to is Rm3 minus Rmb times our mesh vector is equal to EMI. So EMI is just our mesh independent sources. EMD is our mesh dependent sources. And then RMD, mesh dependent. What is our resistor value for mesh dependent? Well, that would come from our dependent matrix right here, or our dependent vector, I should say. So we're going to take our dependent vector. So we're going to make a new page real quick. Okay. So all I'm saying is this right here. So this is just our mesh that our vector that we just created. And we need to figure out what we're going to do with this to separate out into resistor values and currents. Well, we know we're working with a 4x4. I say 4x4 map, I mean our original resistive map, it was a 4x4 matrix because there were 4 meshes, meaning we'll have 4 rows and 4 columns. Same thing here. Same thing applies to our R and D. There's only 4, there's 4 meshes, meaning we'll be working with a 4x4 matrix as well. So what do we do here? Well, we know mesh 3 and 4 are the ones being primarily used for our dependent sources in mesh 1. So what's going to happen is we need to figure out, well, where exactly is it appearing? Is it appearing in mesh 1? No, there's no relation to mesh 1 given our dependent source. Same thing for mesh 2, but there is IM3 and IM4. So all that means is whenever you take it apart, this is linear algebra coming into play and how matrices work now. All we're saying is Rm has been distributed by that. So if you were to distribute Rm into our original equation, it'd be Rm times mesh the current of mesh 3 minus Rm times the current mesh 4, which you're just seeing this. I'm going to go ahead and draw out our mesh vector just so that everyone can see what's going on. Most of you guys should be in Cal 3 or linear algebra and in differentials, either or. You specifically in linear algebra and differential course, you guys should be have passed hopefully how to do matrix operations. If you need help with that, by all means come in and I can assist you with getting some of those basics down, as this is something you'll be seeing a lot. So I really want to make sure you guys know how to do the matrix operations, but this is how it will be. Same thing for mesh 2. What we're doing is, hey, we're distributing it out and seeing where exactly our mesh is. I mean, what is happening with our dependent sources. In this case, in mesh 1 and mesh 2, nothing's really going on there. Based off our substitution we did for I7, we know it would be this behavior for mesh 2 given our RM. Same thing for mesh 4 of how there is a dependent relationship in mesh 1 and mesh 2. We're writing that there, but nothing's happening between mesh 2 and 4, so we don't have to write anything there. And then what about mesh 3? It's 0. Well, that means there's nothing influencing our dependent sources, therefore it's just going to be straight zeros all over the place. So finally, this is our RMD, and based off what we just wrote down previously, where our original resistor map is subtracted from our resistor map for our dependent sources. So we're going to go ahead and do that right here. We're almost done. Just bear with me. It's almost 4 minutes to 6, so we should extend by then. So all we're saying is our final map is going to be this. It's going to be 5, 1. This is where our first resistor value is going to be. It's going to be negative 2 plus Rm. Rm right here, because we go back to our first map, or it is just saying 0. There's no shared component between mesh 4 and 1 right here. What I'm talking about. But based off our formula, subtract our dependent resistive network from our independent one, the one that we created originally. So that's why this value right here is going to be R of M. Since we're doing the double negative and positive, that's how we get that. Same thing through here. We're just going to go through and fill in our resistor map. So there's zeros there, meaning that the first two elements will be the same. This is where it will get a little different, just going to be 4 minus R sub M. And then same thing here, 1 plus Rm. Same thing here. This actually will be the same as mesh 3. Mesh 3 showed no influence in determining our dependent sources. And then mesh 4 had some influence as well. So it would be positive R2 here because it's again subtracting it, turning this original negative right here into a positive one. And here the negative 1 plus U R2, where the 1 came from. our -1. So again, -1 minus our r sub mu. We can go and take out the negative and say, okay, it's just equal to that. And then it'd be -2 here and 6 because there's zeros in our dependent map. These will just carry over the same values. We have our mesh network here. Mesh vector, and then all we're saying is, hey, these are our independent sources now. So we said negative EG was in mesh 1, so it's going to be a -2 here, 0. EG was also shown originally. Now map here, so this is what I'm looking at right now. -2 will be right here. There's no independent source, so this vector will be the number that will be 0. For this element right here, it would be 2 and 0. So that is going to be our EMI map. EMI vector. There it is right there. There it is right there. So now we can go ahead and substitute in RVM. RVM originally equals to 4. So now, everywhere we see RVM, we're just going to go ahead and substitute that in. Oh, I forgot. So I'm going to look right up here. RVM is equal to 4. Mu is, I believe, equal to, I believe it was 2. Yes, mu is equal to 2. Equals 2 volts. And 6, if you have to go, by all means, this is being recorded either way. We're going to substitute in our final values here for R of M and mu. So wherever you see R of M, add in a 2 and then simplify it down. So it'd be -6, 4, right here, the same two values, -1 and 9. R of M should be 4 minus 4, 0, so that'd be 0. 1 plus 4, 5, -5 here. -2, -4, nothing happens there for row 3 as mesh 3 have no dependent sources or anything influencing any of our sources. And then for 2, it will be for mesh 4, so mu R2 is just equal to, well, let's go look. R2 is just equal to 1 ohm, mu is equal to 2, so 1 times 2, which is 2. And then same thing here would be 1 plus 1 times 2, so 1 plus 2 is 3. -3 will go here. -2 and 6 times I am 1, I am 2, I am 3, I am 4 is equal to our independent sources, -2, 0, 2, and 0. This is our final equation. So this is where you guys have to play your own part, okay? So you can solve this however you want. Most people though will probably have maybe a TI 84, maybe a TI 89. If you already have maybe a Inspire already, that's cool. All of these can help you with your matrix math. So they skip all of the linear algebra for you. But if you don't have that, you would really have to sharpen up on your linear algebra skills because how you solve this matrix is because the goal is to find the currents going through our meshes, right? So we have to isolate this. You guys will, if you read Dr. Russell's materials or are currently taking the linear algebra and differentials math 3319, you should know that to solve this, there are plenty of ways. You could do maybe Kramer's rule, maybe find the inverse of it, the inverse of our RMP minus RMD matrix, which is this one right here. So let me actually write out the final numbers, what they mean. IM, and then E, I. There you go. That's our final just equation there. I do see a question. Give me 1 second. My bad, I did not see your questions, Jason. Okay, so let me real quick go through my just little snippet here. Basically, all I'm saying is you have a couple options. You either can do this by hand and really understanding your algebra to go ahead and solve for the current vector, which are the values of each current in their respective meshes, or you can use a calculator and tell it to be doing your algebra for you and do it that way instead. Either or will work. Doing it by hand though is a little more risky just because there's a lot more that could go wrong. It adds a whole lot of more work, but it is still doable. And finally, using whatever method you feel like using, because I do not have the time currently to show each and every step. We find our mesh values. This is what you should get. 132. I need 1 second. This one children's 182.8571 97.14286 305.784 and then 211.4286. All of this is in milliamps. Any negative just means whatever direction you chose for that mesh is flowing the opposite direction. Meaning mesh one, since you got negative there, tank was flowing the other direction, everything else was set correctly originally. That's just how to interpret those values. But again, the real point I want to emphasize is a lot of this was just taking it one step at a time. So the final recap here, you can choose, I usually like writing out the basic behavior of each mesh, then going ahead and using that to set our foundation for it, figuring out how our dependent sources are influenced by their respective counterparts. So for I7, we said that it's equal to mesh 3 minus mesh 4. Since mesh 3 went with our current flow and mesh 4 didn't, we assume that difference there. We could assume the other way too. It just depends. Your convention and which one flows through, which one follows it. Again, you refer back to Dr. Russell's materials. If that is unsure or come to me in the office hours, send me an email and I can clarify that. And then for I7, same thing. Not I7, B2. Up here, we're just saying voltage is equal to the resistive value, so R2 times our current difference, where mesh 2 is going to be used as the bigger number and mesh 1 is being subtracted from it. Again, with Dr. Russell materials would explain why exactly that is happening. Examples also go through that. We go through, substitute in, separate our dependent from our independent sources. And finally, we have our final matrix. We go through, substitute in our known values, R sub m is equal to 4, mu is equal to 2. Then using whatever method, whether it be a calculator, maybe Kramer's rule, or you can find the inverse of the matrix by hand, whichever one, you get the final mesh values right here. And that was the whole goal of the question. Solve the main for the mesh currents. And that concludes our circuits 1 review. Do you guys have any final questions for me? If not, I'm going to go ahead and end the recording here.